go and introduce our esteemed and special guest today. I would like to ask how many of you folks are expecting to graduate around the horizon of 2028? Just roughly? Maybe at least half of the class, right? So I guess just 1 hour ago, we actually wrapped up a very exciting event, hosting our guests from SK Hynix, including their CEO. So they announced a very exciting development right here in Indiana, which basically will be their second home in US for the leading edge memory chips production, what we call HBM. I believe our guest speaker today will shortly introduce this technology as a core of today's AI revolution, right? So by the end of, I guess, 2028, around your graduation, there will be hundreds and thousands of new jobs, exciting career opportunities in this domain, right here in Indiana. So very exciting times indeed, and look forward to seeing new generation of workforce joining this very important evolution, right? So how we can make our future AI models more powerful, empowered by a fundamental technology, which we will talk about today. So if we look at this chart, right, briefly, we have seen an explosion of AI model sizes, right, driven by increasingly large foundation models or transformer models, empowering today's chatbots like ChatGPT. But if you think about the data movement required to move the training data around supporting the training workloads and as well as inference workloads, there is huge demand for memory, right? It's almost like how would you support, like a heavy traffic between West Lafayette and Indianapolis. So it's not only about capacity, right, holding as much data as possible on chip in the system, but also the bandwidth, right? How do you communicate through all these tiny but powerful cores inside of a GPU in the data center and at edge devices? So it's almost like if you expand your number of lanes for the I-65, right, from West Lafayette to Indy, from 2 to 3 lanes to, let's say, 8 or 16 or even more lanes, you will get a much better traffic, right? As a result, your efficiency will be higher to support many of these emerging AI workloads, right? And at the core of this technology, our guest speaker today is Dr. Hosik Kim. Dr. Kim is the Vice President and Fellow of the Memory System Research at SK Hynix, one of the leaders in the memory chips, right, memory technologies for today's AI hardware revolution. It's our great pleasure today to have him on campus to co-announce our special development in Indiana for the future jobs and opportunities for you folks, as well as giving us this very exciting lecture and talk about what's really behind this wave of AI revolution and what's the role of memory technologies especially behind SK Hynix. Let's welcome Dr. Kim.
Thank you, Professor Lee, for introduction. My name is Hosik Kim. I'm leading research, memory systems and pathfinding research at SK Hynix. My team is based in San Jose, California. So I was originally based in Seoul, Korea until last year, but now I'm relocated to San Jose to work more closely with our customers and partners in the ecosystem. So because most of our customers in the AI field are in the United States, hyperscalers and partners like NVIDIA, Intel, all those partners are in the United States. So we need to work more closely together with our customers and partners here. Also, we, as Dr. Lee also as announced it, we had a monumental announcement today. We're going to build a big HBM fabrication facility in the state of Indiana, and we're expecting to open the operation around 2028. It's just about the similar time as you guys graduating. So we're going to have a good jobs and offering a good industry in the east side of Indiana. And then we will also invite a lot of ecosystem partners into this area to make this reality. So memory technologies. So how many have you guys heard about DRAM and NAND? Oh, you know DRAM and NAND. Oh, good. Then how many have you heard about HBM? All right, good number. I didn't know anything about HBM when I was in sophomore freshman. As I said, I got a C on my computer architecture class when I was in sophomore, and now I became a computer architect. So even if you are not good at it right now, you can still change the world with chips. All right. Before I start and talk about memory technology, I'd like to talk briefly about my journey into this semiconductor industry. So I graduated my undergrad school in Korea, and then moved to California to study my master's and PhD degrees. And at the beginning, I studied in electrical engineering, and then later I was attracted to computer engineering. So when I was in college, when I took my first computer architecture class on my sophomore, I didn't feel interested. I was not interested and attracted to computer architecture, so I was poor student. And then later, as I studied electrical and computer engineering in California, I started enjoying my computer architecture class, and then attracted to this area. And then I started delving into that area more and more, and then later studied VLSI systems, and then design automation. And so I got my PhD in computer architecture and then computer-aided design of VLSI system. So during this all years, I learned about computer architecture, VLSI, and software, algorithm, those kind of basic stuff. So I never imagined at that time I would work in a memory industry at the time. And then my interest and specialty has evolved. So after finishing my school, I joined Intel as a CAD engineer. These days, they don't call it CAD engineer. People start calling about EDA, electronic design automation, because CAD, mechanical CAD, architectural CAD, all they call CAD. So they start to differentiate our CAD or electrical system as an EDA system. So I was a CAD engineer because I majored as specialized in CAD when I was in school. So I developed a lot of tools, formal verification tool, timing analysis, and even spice circuit simulators. And then I worked on defining design automation methodology for Intel's own proprietary CPU products. So during that time, I learned about hardware design and software development skills, because CAD is basically a software tool, which is automating design of VLSI circuits. So it's a bit in between software and hardware side. So you have to understand the hardware circuit, and then you have to understand the software and algorithm, computational theory. So it's in the mid. It's the good mix. So I studied CAD and then started my career as a CAD engineer. And then I wanted to do more than that. So I want to involve design myself rather than sitting supporting design as a CAD engineer, tool engineer. So I joined the design team, SoC design team, and started working on SoC design. But leveraging my background in CAD, I started working on SoC design as a design automation engineer, which means using variety of automation tools like EDA tools. I was setting design flow and methodology from spec to final chips. So I was working on the design automation flow. And then I also worked on a pre-silicon verification of SoC and IPs. When you fabricate your design into real chips, it's going to take millions of dollars, right? Hundreds of millions of dollars. So you need to make sure your design is correct. Otherwise, you're wasting a lot of money. So in fact, Intel, for a company like Intel, about 70% of design cycles and resources are spending on verification. So designing verification takes more time and resources than designing itself because you have to make sure. There was a famous incident in 1994, which you probably nobody knows about it. So Intel at that time, Intel developed a Pentium processor and produced it. And then there was a famous floating point error incident. So they actually sold a lot of chips, and then some mathematicians found some error in floating point calculation. And then they recalled it, and then it was costing huge amount of dollars to Intel. And then they started recognizing verification is very important. So they started investing a lot of methodology and automation to verification. So I was part of that. And then moving from design and automation engineer, at that time I decided to go back to Korea for my family reasons. So I joined LG Electronics SoC division as an SoC design engineer. So at the time, LG was very good at mobile phone business and TVs. Nowadays, LG is not doing business in mobile phone, but at the time it was very big. So LG decided to build their own mobile application processor. So I joined the team, and I led the development there. So I moved from automation to design side and architecture side. And then I did a lot of SoC platform architecture design and also developed a memory controller. So SoC needs a memory controller, memory interface. SoC also needs a DDL, DRAM. So all the electronics needs DRAM. So I started designing DRAM controller and DRAM interfaces. That's why I was introduced to memory from CAD engineer to here. So I developed a lot of chips for phones and TVs. If you buy LG TV these days, that is including my IP, my SoC I developed. So I learned that process. I learned during that process. I learned how to design SoC product, actual product, and the high volume manufacturing. High volume manufacturing is also very important. Designing is one thing, but when you actually produce it and manufacture in high volume, it's totally different stories. So you need a lot of things that need to be taken care of. So I learned that product engineering and high volume manufacturing. And then because of this, my exposure to memory controller, later I joined SK Hynix, the currently I'm working for. Now I became a memory systems architect. So I'm currently leading various research and pathfinding activities in the area of memory systems and solutions, including software solutions for mostly data center architectures and AI and hardware and software. So these days, you are relying on, your daily life is relying on a lot of data centers and cloud service providers, right? You are using Google, Facebook, Instagram every day, right? So those, all the services are now being supported by cloud service and data centers. And every data center needs memory. And actually, the most of computing bottleneck, computation bottleneck is actually memory bottleneck. So if you further study computer architecture, almost half of computer architecture topic is about memory architecture, memory system architecture. Because of von Neumann architecture, have you heard about von Neumann architecture? Do you know von Neumann, right? Von Neumann architecture is basically all the data and programming code is in memory, and there is a computation unit and then memory unit. There always have to be a transfer of data between computation unit and memory unit. So because of that definition, all the current computing devices based on that von Neumann architecture concept. So memory is the bottleneck. Well,
adjust that a little bit, because can I see if it's on? Yeah, it's on.
okay. So yes. So if you think about A plus B equals C, right? Let's say you do the computation, right? You need to retrieve load A and B from memory and do the computation. And then again, you have to write back the C to the memory, right? So A plus B is now very quick. Can be done very quickly, right? Now, because of the advance of CPU technologies, they can compute very quickly. But actually loading data from A and B and then writing back to C is taking more time. So all the bottlenecks in the memory interfaces. So I'm working on right now our customer systems. Rather than working directly on the device itself, I'm working on more like memory systems, which is our customer system, like data centers, AI, hardware training, inference system, so that I analyze those systems and then where the bottleneck is, and then mostly it's a memory system, right? Memory bottleneck. So I propose a new architecture and solution how to optimize our customers' system, have better performance, better TCOs, better low capacity, low power consumption. So I propose those ideas, and then we do proof of concept verification with our custom systems, and then basically designing future memory solution products. So my team is responsible for defining a new solution, new next generation products for data centers, AI systems, and edge devices on IoT device. So during this process, I learned about AI system, hardware, and software. Also, I learned about data analytics and database systems, because data analytics and database system is, you may not heard much about data analytics and database system, but today's in data centers, all the data, your Instagram data, Facebook data, all the data are stored in data analytics platform. And then if you want to do AI inferencing service, all the data, you have to retrieve all the data from data analytics and database system. It consumes a lot of memory and storages. So we study data analytics systems and cloud computing, data centers, all those heavy memory users. I learned about it, learned about system. So I evolved from CAD engineer to verification engineer and SoC designer, and now memory systems architect. And I don't know what will be the next, my journey. So I'm personally interested in these days in advanced packaging and interconnect technology at the chip level and server level. So my interest is still evolving, and my personal expertise and career is, I think, evolving. So be curious. What I want to say to students is be curious and open and willing to adapt to new challenges, and then always work to learn. So every time I change my jobs, my change company, the criteria I chose to the next job and next company was what can I learn, right? Rather than just whether they give more money, more salary. That's not my choice criteria. So my choice of criteria was how I can grow professionally, technically, right? So yes. So when I worked at LG at designing SoC, I found that memory is the bottleneck of all the performance. So I started to understand and appreciate the technology of memory interfaces, and then I like to contribute to that. And I like to learn more about memory. So that's how I joined the SK Hynix. And then now I started to realize that, all the bottlenecks and performance gap is between interconnect. At the chip level, inside the chip, there's a multiple IPs, right? The interconnect between multiple IP is also important. And chip-to-chip interconnect is also important. And then in the data center, server node to server node interconnect is also very important. That's actually another bottleneck, performance bottleneck in the system. So everything is very hot topic these days. So I'm personally interested in that area. And then the facility we have actually announced today is about advanced packaging manufacturing facility. So advanced packaging is all about actually interconnect. Packaging, nowadays, packaging requires heterogeneous integration, like logic process, memory process, and due to limitation of Moore's law is actually nearing the limitation. So we cannot scale, and we cannot put a lot of new transistors into a single die anymore. So rather, we have to assemble multiple dies, die to die, right? We have to assemble multiple die, and we are even talking about stacking multiple die in 3D. So that's what advanced packaging facility and manufacturing does. So to do that, everything is about interconnect. How do you interconnect multiple chips, multiple dies? So that's HBM. Actually, that's HBM. So HBM is a high bandwidth memory. HBM is a crucial ingredient of today's AI hardware, including GPU. This is actually picture of HBM, GPU, NVIDIA GPU. The left side picture is NVIDIA GPU. In the center, there's a golden die, right? That's NVIDIA GPU. And then above and below that, there are 3 each, right? Black die, three on top and 3 on bottom, right? That's HBM. So HBM and GPU are tightly integrated together in the single package to serve better, to serve GPU better in terms of bandwidth and power and latency. So that's how you integrate and interconnect between GPU and HBM. So in between, there's a silicon interposer. There's another technology which is integrating GPU and then HBM. And also inside HBM, if you look at this right-hand side, this is a 3D view of HBM. HBM is basically stacking multiple DRAM dies on top of each other. So it goes up to like a 12 high right now, 12 stack. And at the bottom, there's logic die. Logic die is actually include peripheral logic, I/O, MUX, and those kind of logic process, which is communicating with the DRAM die. So that's another interconnect. So we call the TSV, through silicon via. If you see this, this little things, so basically we drill holes in multiple dies of memory chips, and then connecting each other through a metal layer. So that's another interconnect. So this is a particular technology which is very challenging to implement and in manufacturing. So SK Hynix is actually #1 leader in this domain. So that's why current NVIDIA chips, if you buy any NVIDIA GPU chips, 100% of HBM is from SK Hynix. We are the sole provider of HBM. So that's why this HBM is a crucial ingredient of a GPU and AI system. So now that we talked about SK Hynix and memory industry a little bit, so I'd like to show where we stand in terms of top 10 semiconductor makers by revenue. If this is last year's record, so we ranked #6 in total top 10 semiconductor makers. Intel was #1, and then Samsung, Qualcomm, Broadcom, NVIDIA. Actually, we were #3 last year, and then we moved to #6 now because last year was a historic downturn of memory industry. So memory industry has interesting. So memory is require high capital expenditure, meaning it's a very equipment heavy, investment heavy. If you start building a facility, you have to invest like billions of dollars, right? And then let's say you decide to increase the HBM capacity, HBM manufacturing capacity more today, then it takes more than a year. It takes about 2 to 3 years to produce a new memory in manufacturing, because you have to build the fabrication facilities, and then you have to install the equipment. That's why even though we have announced a big investment in Indiana today, the actual operation will be happening in 2028. So predicting future is very difficult. We don't know what will happen in 3 years, right? So this rapidly changing AI world, I don't know what will happen, and then what kind of new processing technology or what kind of new algorithm will happen in 3 years, right? So right now, AI is heavily dependent on GPU and HBM, but will it continue to depend on HBM and GPU in 3 years? Do you know that? I don't know, right? No one knows that. But we have to decide our investment today. So let's say we decide to invest, we forecast that HBM will continue to prevail in this industry, then we decide to invest HBM and expand our capacity, then later, 3 years, actually no one uses HBM anymore, then we're in big trouble, right? So predicting future is very difficult but very important for memory companies. So that's why our team is researching future system, future AI, where this AI will go to help our company to make a decision, important decision, and to predict the future and prepare the future. So last year, because of that, so that's the nature of memory company. Because of that, there is always supply and demand issue, right? So every time we increase our facility, then at some point there's oversupply. Then memory industry goes down cycle, and then later the demand increase. Then we are in short, with supply is in short, and then our prices goes up. Then we make a lot of money right now, and then there's a cycle every 2 years or so. Also, so last year was a historic downturn. So that's why our company's revenue declined to six in the rank. But traditionally, we are within top 5. So, but interestingly, if you've seen top 10, this year Micron has dropped below 10. It was actually Samsung was another big memory manufacturer, and Hynix was another second actually, and Micron was also among top 5 until last year. But now, because of that historic downturn, Micron fall off from this list. And then NVIDIA and Broadcom jumped into top 5, right? NVIDIA and Broadcom was below top 5 before. But NVIDIA is obviously because of GPU. And Broadcom hit up because of Broadcom produced a lot of AI accelerator for bigger companies like Google's and Microsoft. Those kind of big companies are developing their own AI chips, but actually that design service is being done by Broadcom. So that's why their rank went up. So the point I want to make is among these top 10 or top 5 top semiconductor manufacturers, memory companies are among top 5, top 10 companies. So when I was in college or my early career, I didn't even thought about joining memory. I never imagined I would work for a memory company, frankly speaking. I was interested more like SoC design and computer design. And as a CAD engineer is dealing with automating complicated chip design by modern advanced computer algorithm. But memory was, to me, when I was younger, to me, memory looks like it's a fairly structured design and full custom circuit design. So that looks a little boring to me. So I decided to join CPU company and SoC company. And then later, I learned that, memory is very complicated, very sophisticated technology, and also it dictates and then it dominates all the overall performance. And then nowadays, because of this advent of this AI technology, people started to realize memory is a key component. Because all GPUs, as you know, NVIDIA GPU is in short right now. But one of the big cause of that short production is because of HBM supply issue. So they need more HBM. Even though they have GPU production, if HBM is, they don't have enough HBM, they cannot produce GPU because GPU and HBM has to be integrated together in same packaging. So, and there are a lot of AI hardware accelerator companies and startups, including hyperscaler, many big tech companies like Google, Microsoft. Those companies are also building their own AI chips. They try to diverge from NVIDIA. But they all need, at the end of the day, they all need HBM. They realize that all the bottlenecks in memory interfaces. So we are we need to expand our production of HBM. So that's people started realize the importance of memory technology, and then we are actually working with many companies, many chip companies, including hyperscalers, NVIDIA's, Intel, startups. They all request more memory more memory supply from us, and then they want to research together to innovate the AI hardware system together because they realize that memory is a key component. So that's the point I want to make here. And then talking about memory company and SK Hynix, we are second in DRAM market. Samsung is about 40%, we are about 35%. And then there's a NAND business, NAND. So do you recognize the difference between DRAM and NAND? DRAM is a volatile memory. So it's basically, it's used for computation. And NAND is a non-volatile memory, meaning that once you store some data in NAND, even if you turn off the power, the data is reserved. So NAND is used for storage, right? So that DRAM is used for computation. So if you think about your iPhone, if you store your photos, those photos will be stored in NAND. And then if you want to do text messaging, if you want to upload your posting, or if you want to do something gaming, then those data is from DRAM. So DRAM is for computation. But NAND has NAND device can have a higher capacity. They can hold more data in a smaller spaces. But NAND interface is slower. Accessing data from NAND is taking more time than DRAM. That's why DRAM is used for computation. And DRAM is more expensive. And NAND has a relatively higher capacity than DRAM, and then more cost effective. So we are also number 2 to 3, depending on the time. So we are about number 2 to 3 in NAND business right now. So memory, I said, memory is everywhere around our lives, right? Memory goes to cell phone, AI system, and even head-mount display like Oculus, and your cars, automotives, computation, data center, everywhere. Everywhere needs. If you have compute device, memory is everywhere. So now we are relying on, our life is heavily dependent on data centers and cloud services, right? They are heavily using memories and DRAM. Data centers are crunching and producing massive amounts of data every day in real time. So even though they are using a lot of memory and data, but they are also making new data every day and every time, right? You put more data, especially in this AI world, with generative AI technology, generative AI itself is producing new data, new information. So that all goes to memory and storages. So this AI, big data, cloud computing all requires increasingly higher bandwidth and capacity from memory to manipulate this ever-growing amounts of data. Higher bandwidth meaning, as Professor Lee talked about, they need more data in a certain period of time. Like in a second, we need more data to be consumed and processed. That's high bandwidth. And capacity is a large amount of data to store. However, this memory is very expensive. If you think about server costs overall server costs in data centers, about 30 to 40% of data center server cost is a memory cost. That's why this memory company is making good money and listed among top 5 to top 10 companies in overall semiconductor company. So nowadays, because of this data-centric world is heavily relying on memories and the data centers and AI. Now, memory takes the center stage of the computer game. It was in the center from the beginning, but for the time being, people concentrate on CPUs and GPU. Now, because of this AI systems, AI world, people started to realize that memory is a key component. So memory goes to the center of the stages. Now we call it memory-centric computing era. So what makes AI? Data makes AI, right? So to make AI system smart, you need to train your system. Machine learning is training your system and data. You have to, machine has to understand your action, your history, right? Everything. That's data, in the form of data. And then data is making AI possible. And also, again, AI, with generative AI especially. Generative AI is making new data and producing new data every day, every hour, every seconds. So there's a cyclic transformation of data. Data makes AI, AI makes data. These data are all reside in memory devices. So, however, so this AI and machine learning technology is a very memory-intensive technology. It requires a lot of memory operation, data read and write activities. This AI algorithm requires a large data sets to train this neural network model, and also GPU. When GPU do inference operation, GPU requires high bandwidth, high capacity memory for this memory-intensive training and inferencing of this large language model, right? Large language model has a huge amount of model parameters. Those model parameters need to reside in memory, especially in HBM, to be processed by GPU. So this is a heavily memory-dependent technology. So now, in order to make this AI system very costly, I mean, AI system is very expensive system right now. So it requires, if you want to do training, it requires like thousands and tens of hundreds of thousands of GPU, which is costing a lot, right? So we need to find more cost-effective way to process this AI training and inferences. So to do that, memory needs to play a key role to make it more high bandwidth and high capacity in more cost-effective manner. And then we even have to design the whole system together with the GPU companies and CPU companies to better utilize our memory, rather than just focusing on producing more capacity and more bandwidth into the memory device itself. We have to work with our partners and AI systems overall. Sometimes we have to work with the software algorithm guys to innovate the way we handle memory traffic in computation. So that's actually my team is doing, right? My team is not working directly on the DRAM itself. We are working on the software ecosystem and overall system level. So AI is still, but AI, as NVIDIA CEO Jensen Huang said, AI is still on the beginning, at the beginning of the workload stages. Actually, AI started to boom last year, right? We talked about DNN and computer vision and speech recognition from several years ago, but suddenly it boomed up because of this ChatGPT announced last year, right? Because ChatGPT, everyone is talking about AI technology, AI system, right? And normal people like us started to pay attention to AI. Until last year, we heard about AI, but we didn't really use AI, right, itself. But nowadays, everyone is using ChatGPT right now. So it's going to go up, right? At least for 10 years, right? Jensen predicted that this AI boom will go like more than 10 years, and then this is actually second year, right, of this AI boom. So we need to continuously invest hardware system that makes AI service possible, right? That's why OpenAI has invested, this publicly announced that they are going to build a whole ecosystem and whole hardware system themselves, and then it started to invest, astronomical amount of money to their hardware system. However, I don't know this can be sustainable, right? It simply needs nuclear power plant to support these AI training data centers. And then we need like millions of GPUs, which is very expensive these days, and then a lot of power, real estate to build that data center in this land. So we have to figure out how to make this AI hardware system more cost-effective, consume less power. So in that innovation, GPU guys also has to invest a lot, and then software algorithm, AI model developer has to also invest a lot. But we have a memory company. Memory technology also has a key role and responsibility to make it more cost-effective, and we have to lead the innovation. So with that, only with that help of AI memory, advance of AI memory, we can truly boost up the efficiency of AI system. Otherwise, we can't sustain this kind of system anymore. I don't think so. So to run a typical data center, they say about 500 megawatts of electricity. This is about half of a nuclear power plant. Typical nuclear power plant is 1 gigawatt hour, 1 gigawatt to hour, but 500 megawatt to hour is about half of them. But now our advance of our LLM models, if we talking about GPT-5, GPT-6, then the power cost, the amount of power consumption will go exponentially. So we probably cannot sustain and support. So that's where we, as a semiconductor engineers, including GPUs, CPUs, and AI memory, we have to innovate and then brainstorm out together, working with the software engineers. So with that investment into AI memory solutions, SK Hynix has a multiple variety of AI memory solution portfolio. The most important thing is HBM. And then HBM is very essential part in data center AI. But nowadays, people start talk about edge AI or on-device AI. So if you want to use AI these days from your phone, your request actually goes to data center and cloud service providers. And then the AI inferencing and training is done from the data center and then retrieved back to your device. But people start thinking that might be inefficient, right? Why don't you just process your AI inferencing at your phone? That's why we call what we call on-device AI. To do that, we might need less bandwidth, but we definitely need a higher efficiency in power consumption because smartphone cannot sustain that high power consumption. So that's low power memory is important. This low power LPDDR memory is coming at. So this low power is more like a device level or your notebook, laptop level AI solution. And then you also need high capacity of memory to store the huge amount of training data rather than computation. So that's why this high-speed, high-capacity storage device is important to store the trained data. And then we have to also innovate how we compute. So this is an interesting point. I told you earlier about von Neumann architecture. Von Neumann architecture has a distinct differentiation between the compute logic and then memory logic, memory unit. But people start to realize that, why don't we just do the computation at the memory inside the memory, right? Rather than moving data transfer back and forth between a compute and a memory, we can just do computation inside the memory. Memory has a very structured and multi-parallel design inside the chip. It has arrays of bank and cells, rows and columns. So it is inherently very parallel structures. If we can do little computation inside that memory cells and banks level, then we can we can utilize this heavy, high internal bandwidth. So that's where we start to thinking about processing in memory. We have a first product. It's not in mass production. It's something like a prototype kind of concept product. But memory companies start to think about this processing in memory devices. We have a couple of years ago, we have announced GDDR-based memory processing in memory. We call it AIM. AIM stands for accelerator in memory. This specific device is designed for AI computation. So AI computation is, if you think about this AI computation theory a little bit, this, at the end of the day, it boils down to matrix multiplication and accumulation. So it's all about matrix multiplication and addition. Multiplication and addition. That multiplication and addition is simple, rather simple logic, but it requires a lot of data computation in parallel. So that's a very good target example of processing that can be done, that can be better done in memory. So that's PIM. Oh, we have time, right? So that's high bandwidth memory. I'll move fast. So this is, I talked about high bandwidth memory. We achieved the high bandwidth by adding more I/O pins to memory and then stacking multiple DRAM dies so that we can achieve higher bandwidth and higher capacity. So I'll move fast, and then even though we are expanding bandwidth and capacity by stacking multiple dies in 3D manners, so chips still need, SoC and GPU still needs more bandwidth and more capacity. So that's why we start to integrate multiple HBM cube around this GPU SoC. And depending on the application, training requires more capacity and more bandwidth. So we, in training system, typically we add more HBM cubes, and then inferencing we put less HBM cubes. So HBM market forecast, HBM market will continue to grow even more, even in a higher rate than AI accelerator, because AI accelerator, the requirement, the amount and the number of HBM cube required by AI chip accelerator is continuously growing. So we are expecting even higher growth rate. So I also want to mention about new opportunity with CXL. I talked about HBM a lot, but CXL is a new opportunity for memory companies and new opportunities for data centers. So basically, between CPU and DRAM, they all require parallel interface, DRAM interfaces. If you look at CPUs, there are around the CPU die, there are DRAM interface, which is parallel interface, which is very costly and then takes a lot of spaces. So even if you want to add more DRAM, you cannot simply add more DRAM because it will explode the chip size, so which is very costly. So, but however, so we need more. SoC are adding more computation core inside the CPU and GPUs. They require more capacity and more memory bandwidth, but there's no way to add more memory. So the system architect, what system architect do is they simply add more GPU. They require more GPU, not because GPU computation needs more resource, just because they need more memory. So in order to get more memory, they have to replicate and increase the number of GPUs to consume more memory. So, which is very costly and inefficient. So people have proposed a new standard using a new interface to add more memory besides the DRAM channel. So CXL is basically utilizing PCI Express lane, which is traditionally used for I/O devices, I/O peripheral device extension. Then the industry actually proposed the idea about the CXL interface to add more memory. So Because of this, there's a new area of growth and opportunity for memory companies to expand and then contribute to this system. So yeah, I will, I have a little bit of time. So because of this CXL, it will create new opportunities for compute system, overall compute system, which is beyond what is possible today in server platform. Because of the new interface, we can have a way to expand memory, bandwidth, and capacity. And with the CXL technology, memory controllers move from CPU side to memory device side, so we can have more room for differentiate different memories. And then we can also it can easily integrate computation core, processing core with memory. So it will make possible it will make computational memory possible. And finally, it will also allow computer system to disaggregate memory from compute node to memory node. So SK Hynix is actually preparing a new kind of concept memory solution products to address each of these, and then working with data centers and hyperscalers to test and do the proof of concept work with our customers. And then I say this will be a big change in big shift and change in system architecture and data center architecture in 5 years, from 5 to 10 years right now. So yeah, so memory. Now this is a very great opportunity. It's a good time for all of us to work in the memory industry and then drive the innovation together in this data-centric world. So HBM and AI memory solution will be the key enablers of AI technology, and then the CXL will create a whole new way to design and use our memory system in data center structures. So this is a really exciting time to work in a memory company and memory industries. So having said that, if I want to briefly talk about SK Hynix, we have 4 manufacturing sites in Korea and China until yesterday, and then we have announced today a big announcement and investment in the United States, in the state of Indiana. We're going to have a big manufacturing site in the United States, and then 4 R&D centers located in US, Taiwan, Japan, and Korea, right? So there's a plenty of opportunity for all of you can contribute to this memory industry. And yes, this is a facility here Professor Lee talked about today. We had a monumental announcement that we're going to build a big HBM packaging fabrication and also research fab and R&D fab here in Purdue Research Park, Purdue Research Science Park within West Lafayette. So it will be about 90 acres in Research Park, and then starting the second half of 2028, we're going to do mass production of HBM here in the Indiana state, and then we are expecting about 1,000 of engineers, R&D engineers, to this manufacturing facilities. So by having constructed, by producing new memory manufacturing fab in the United States, so we can better work with our customers and partners, and then we can build the ecosystem, whole industry, semiconductor ecosystem in the United States, and then we can hire more talented people like you, right? And then contribute to this industry together. So Hynix has requires many engineers from different backgrounds. About 30% of our engineers are electrical engineers, but about 18 to 20 people are chemical engineering, material science, mechanical engineering, and even these days, computer science engineering. Computer scientists is very important to work with the AI systems. So we have a number of opportunity and from diverse backgrounds. Specifically, the SK Hynix in California, San Jose office, we are looking for these kind of engineers right now. There's immediate career opportunities. I know you guys are still, undergrad and first year, second year students, but we are expecting and recruiting actively AI, ML system architect, SoC designers, system software designers, not just a DRAM and NAND device designers. We are actually working in a Linux kernel community because if we want to, if we produce a new type of memory devices, that needs to be supported by Linux kernel, right? Current Linux kernel is only supporting DRAM and NAND. But let's say we propose a new tier of memory between DRAM and NAND, which is not being supported by Linux kernel right now. So we have to develop our own Linux kernel and then propose and then contribute to the Linux kernel community to support let ecosystem to support this new type of memory devices. So that's why we need a system software engineer, Linux kernel developers, those things. So that's it. So that'll be my lecture today. So please join us to change the world with chips. So thank you.